Well, I'm very pleased to introduce our closing speaker, John Holdren, who is the President Obama's Science and Technology Advisor and the Senate-confirmed Director of the White House Office of Science and Technology Policy. You can think John is the longest-serving science advisor and head of OSTP, he will have served the full term of 2 terms of president, and I think you're the only one on that. But also he's had the pleasure of serving with the president, who is really interested in STEM education, technology, and the vision and entrepreneurship. And many of you here have had the opportunity to meet with him, and also calls upon John for many technology and science issues, and which has really been good. And so John spent most of his career as a faculty member at University of California, Berkeley, and at Harvard, where he led interdisciplinary programs focused on energy technology and policy, global environmental change, nuclear arms control and nonproliferation, and science and technology policy. Well qualified for his current job. So thank you, John.
Well, thank you, Maxine, and thanks to all of you. It really is a pleasure to be here. It is a little awkward to be giving closing remarks at a meeting that I have not attended, and that's a bit of a trick. You'll have to forgive me when I repeat things that everyone has already said, but you know that saying, everything has already been said, but not everybody has said it. So I have the opportunity to remedy that this afternoon. Let's see which way this thing goes. What do I aim this at to get it to change? Where do I need to aim it?
There we go.
So you have to aim high? Whoops. No, I already, that's where I want to be. Okay, good. So I start with the observation that when the NSF's Engineering Research Center program was established in 1984, its focus, and this is taken directly from Pramod Karganekar's presentation of last December on the history of the program, its focus was on multidisciplinary engineering, research, education, and workforce development in partnership between academe and industry. And it seems to me that, and I'm sure that much of this has been discussed at this meeting already, that there are some clarifications and updates that are now required. One of them is that we really need to understand multidisciplinary engineering research to include not only diverse engineering disciplines, but also physical sciences, life sciences, and social sciences. So it's a broader definition of multidisciplinary than they may have started out with. Secondly, I think it's very important that multidisciplinary, that is the engagement of multiple different disciplines, be augmented by interdisciplinary, which really means having some people who are trained to communicate across disciplinary boundaries and to integrate across disciplinary boundaries. One needs lots of specialists, for sure, but one also needs some folks who specialize in putting the pieces together. The third point is that partnerships really need to be expanded from just academe and industry to include government at various levels and to include civil society as funders, as facilitators, and in fact as representatives of the user communities who are going to benefit from innovation. Now if we can get this right, see, I have to aim high. So I want to call them multi-interdisciplinary centers, which I'll abbreviate by MID to get both the multi and the inter in there. So there are any number of grand challenges that require multi-interdisciplinary solutions. Everybody can make their own list. Probably many of these have been discussed in the meeting already today, and certainly everybody in this room could add a few to this list. This is just representative. It's my list of some of the big juicy ones where clearly these kinds of solutions are required. So President Obama, when he came into office, was already imbued with the proposition that innovation is crucial to improving the human condition worldwide and in the United States. I couldn't tell from his resume where he got it, but he started out very savvy about science, technology, engineering, and innovation. And he Very early in his administration, with input from OSTP and from PCAST, his Council of Advisors on Science and Technology, in which, by the way, Maxine Savitz is the vice chair and a very active member. With the help of those groups, he put forward initially in September of 2009 what we called the American Innovation Strategy. And it had a number of components which, again, relate to where we are now trying to go with multi-interdisciplinary engineering centers. The first set of pillars, if you will, of the innovation strategy was to invest in the fundamental building blocks of innovation, educating Americans with 21st century skills, including, of course, particularly STEM skills, strengthening leadership in fundamental research, which means not only funding the research itself, but nurturing the institutions that do it, building a leading physical infrastructure. That means high-performance computing, it means broadband, it means sensors, it means space platforms, it means accelerators, and much more. Not necessarily the most glamorous part of investing in innovation, but absolutely essential. And it means developing an advanced information technology ecosystem. A second component of the strategy was promoting market-based innovation, and the elements of that are indicated here. Interestingly enough, it took us until last December to finally get the research and experimentation tax credit made permanent. The President said in his address to the National Academy of Sciences just a few months after he was inaugurated in April 2009 that he wanted to make the tax credit permanent, and we failed every single year until finally the bipartisan budget agreement in December of 2015. We finally got that one done. A variety of initiatives launched to encourage innovation-based entrepreneurship, reform intellectual property rights policy, promote innovative, open, competitive markets, all fairly obvious, and a focus on catalyzing breakthroughs for national priorities, which in many cases have substantial public good components, and therefore there's a strong rationale for government playing a role in getting these things done. Clean energy, biotech, nanotech, advanced manufacturing, and of course their intersection, space applications, healthcare technology, educational technologies, all focuses of specific initiatives that this administration ended up launching. Again, many of them recommended by PCAST and fleshed out by PCAST and then subsequently embraced in detail by the President. But it's important, there are a number of cross-cutting aspects of those three pillars that the administration has emphasized. One is supporting scientists and engineers early in their careers. This has been a real challenge in a time of fiscal constraint. As I think most of the people in this room know, for example, at the National Institutes of Health, the average age of a principal investigator at first NIH grant is about 45. This is problematic. Only about 1 in 6 proposals to NIH get funded at all. That is also problematic. A second focus is increasing the engagement of women and girls, and by the way, underrepresented minorities in STEM fields. Commercializing university research, figuring out how in partnership with industry to shorten the transition from discovery in university research labs to widespread application. And finally, particularly germane, of course, to this meeting, multidisciplinary research and high-risk, high-return research have been emphases. So I want to point out that we have actually been doing quite a lot with multi and interdisciplinary centers already in this administration, early in the 21st century. One example is the Department of Energy's Energy Innovation Hubs. The quote here is taken straight from the DOE website on the hubs being modeled after some characteristics of the weapons labs, of the Lincoln Lab, of Bell Labs, the DOE Bioenergy Research Centers more recently. And there are now 5 of them, 5 of those energy innovation hubs. One focused on advanced light water reactors and other nuclear energy challenges, one focused on artificial photosynthesis, one on energy efficient buildings, one on energy storage, and one on critical materials, all going strong. And another set of multi-interdisciplinary centers have been developed under the auspices of the National Network for Manufacturing Innovation. There are 8 of those centers currently in operation, 7 more to come by the end of 2016 to meet President Obama's goal, his stated goal when this program was launched, of having 15 of these by the end of the administration. The most recent one to be awarded was launched April 1st by Defense Secretary Carter in Cambridge. The winning team, led by MIT, had 89 manufacturers, universities, and nonprofits engaged in it. Further awards are coming. And on the right of this particular slide are just enumerated some of the successes that these multi-interdisciplinary centers have achieved. There are, as I noted, 8 of them. You probably can't read this all around the room, so I'll just note that the 8 from left to right: hybrid electronics, digital manufacturing, light and modern metals, additive manufacturing, advanced composites, photonics and integrated circuits, smart power electronics, and revolutionary fibers and textiles. That's the most recent one, again, led by MIT. And as noted here in the text, they are already delivering. So let me make a few observations on what we need going forward to widen, to scale up the kinds of success that we've been having with multi and interdisciplinary centers. One is we need to boost STEM inspiration and preparation in the pre-college years, and above all in technology and engineering. We have some science and math K through 12. We don't have very much technology and engineering at all, and we need to do better in persuading our young people at a time when they're really making up their minds about what they want to do and what they want to be, that engineering and technology are important, they're exciting, they're rewarding. We're not getting that job done yet, and we need to get much better at it. Secondly, we need to accelerate a revolution which has started in undergraduate STEM teaching, which has had the shortcoming that it has been, in many respects, particularly in the first 2 years of introductory courses in science and engineering and math, boring. All lectures, all fundamentals, none of the excitement that comes with really doing engineering, doing science, doing math. There is a transition underway to what we call active learning, much more student engagement, fewer lectures, students working in small groups with tutors and professors to solve actual problems, and getting even freshmen and sophomores into laboratories in their first 2 years. Right now, we're still losing about 60% of all the students who enter college in this country intending to get a STEM degree. 60% of them don't get a STEM degree, only 40% do. This is an enormous loss to the innovation community. Third thing we need to do is we need to grow the interdisciplinary graduate teaching and training pipeline. We have basically large, very capable communities able to populate the multidisciplinary parts of these operations, but we don't have enough programs around the country that are explicitly focused on training that relatively modest subset of the STEM graduate student population who want to become integrators, who want to become experts in putting the pieces together. The Energy and Resources program that I helped found at Berkeley in 1973 is one example. The Technology and Policy program at MIT is another. The Engineering and Public Policy program at Carnegie Mellon is a third. I could name a few more. The number is growing, but we need to do more of this in order to get the inter as well as the multi into the centers as we expand their number. We need to continue to strive for greater inclusion and success of females and minorities at all of these preceding steps. We still have, and this is a focus of some of the folks in my office in OSTP currently, there is still a lot of built-in gender bias in the STEM fields that discourages girls and young women from believing that they can succeed in engineering, that they can succeed in science, that they can succeed in math, that they can be leading innovators. We need to work harder to root that out. We need to make sure that young women and girls and underrepresented minorities get the mentoring they need to understand that they have every opportunity to succeed in these fields. as well as others. We need to propagate the understanding that not all experiments succeed. There is often a tendency to penalize failure. If we are not failing some of the time in our work in engineering, in science, in innovation, we're not trying enough. We need to maintain and expand the culture that we learn from failure, start again, and do better. And my experience, I travel around the world. I'm responsible for 6 ministerial level science and technology cooperation agreements with Brazil, China, India, Russia, South Korea, and Japan. I think the United States actually does better than any of those countries on understanding that not all experiments succeed. They envy us in that respect, but we need to do better still in terms of creating a culture in which it's understood that if you're trying enough, some of those attempts will not succeed, at least at first. And finally, we need to overcome the barriers to adequate investment in basic research. There is a rather appalling tendency that is evident today in some parts of Congress and elsewhere to say we should take money out of basic research, put everything into biomedicine and public health, into clean energy, into national defense and homeland security, into climate change, applied stuff. The applied stuff is enormously important. Innovation, which this meeting is focused on, is about innovation to get important things done in society, but basic research is the seed corn on which future innovations are going to be based. And if you eat the seed corn, ultimately you're going to starve the system. We've had folks in Congress proposing that every NSF grant should be defended by the NSF director to the Congress in advance as to how it will help the economy, public health, or national security. I mean, this, if you read the Organic Act of 1950, which created the National Science Foundation, the first responsibility of the National Science Foundation is the progress of science and engineering. The progress of science and engineering, which requires investing in fundamental research, in basic research in those domains. We have to do a better job of educating the public and educating the Congress about what you might call the innovation pipeline, but of course, as we in this room all know, it's not really a pipeline, it's a set of feedbacks between all the levels from fundamental research to innovation and scaling. And if we fail to sustain the level of societal support for basic research that society's needs require, we will suffer in the long run. That's it for me. I'm happy to take some questions.